In this question, we're asked which statement is true regarding atomic number, atomic mass, and mass number, and only one of these statements is true. So let's step through them one by one and decide whether each is true or false. First statement here, different atoms of a given element may have different mass numbers. Is that true? Well, yes, absolutely that's true, right? This is exactly what's going on with isotopes, which have the same atomic number and correspond to the same element as a result, but have different mass numbers because of their different numbers of neutrons in the nucleus, right? So actually, straight away, this is a true statement. But let's verify why the others are false. Atomic mass and mass number of a given isotope are equivalent. This is false because the atomic mass takes into account things like mass energy corrections. And so that's not going to be an exact integer. It's going to be a decimal value. And so the mass number, which is the exact integer count of nucleons in the nucleus, will not match the atomic mass in general. Atomic mass is the weighted average of the mass numbers of the stable isotopes of an element. Not exactly true, and this one may be a little bit subtle. What's described here is the average atomic mass, not atomic mass referring to a single specific isotope as we just described in the previous statement. Next statement says two atoms of different elements may have the same atomic number. We know this is false because the atomic number is what defines the elements, and so two different elements by definition have different atomic numbers. Next we have all atoms of a given element have the same atomic mass. Well, this is false because, again, of the existence of isotopes. This is worth copying down, that because we have isotopes which have different mass numbers and different isotopic masses, different masses for those specific isotopes, the atoms of a given element display different atomic masses in general if that element has multiple stable isotopes. And then finally, mass number is the weighted average of the masses of all isotopes of an element. Again there, what's described is the average atomic mass, not the mass number, which is an integer value just counting the number of nucleons in the nucleus for a given isotope. Question 6 here is all about isotopic abundance. We're thinking about a hypothetical element with two stable isotopes, A and B. We have isotope A with a mass of 49 AMU and isotope B with a mass of 47.029 AMU. And we're asked, what is the average atomic mass in atomic mass units if the abundances are as they're listed here? And let's write out these abundances to make things a little bit more clear numerically. So what we have here is that in a given sample, 47,337, very odd number, but there you go, 47,337 atoms in the sample are A in a total of 100,000. So what I'm actually going to do is just shift the decimal place. 47.337 divided by 100 is equivalent to 47,337 divided by 100,000, right? And so another way to express this is that the sample is 47.337% A, and the balance, the remainder, must be B, right? And if my math skills serve me right, that's 52.663% B. And what we want to know now is the average atomic mass of this element. How do we think about that? Well, we take a weighted average of those isotopic masses, where the weights correspond to these isotopic abundances. Expressed in decimal form is probably the easiest way to go about doing this. So, for example, we have isotope A, and let's underline that in red and write that out in red, 49 AMU, and in a given sample, 0.47337 of 1, if you like, is isotope A. And for isotope B, let's do that in blue, we have a mass of 47.029 AMU, and the abundance there is 0.527. 663. And multiplying this out and adding the two terms together is going to give us the average atomic mass. Doing this math and multiplying everything out, we end up with 47.962 atomic mass units for the average atomic mass. And as kind of a sanity check here, this makes sense. The sample's roughly half A and half B, and the average atomic mass at 47.9 is close to halfway between 47 and 49. So it makes sense here that our average atomic mass is about 48 AMU. Finally, our last chapter 2 question asks about elements on the periodic table and finding those elements and determining the element symbol for the following elements. So let's use the periodic table to do this. You're going to have access to the periodic table. Might as well use it. So the first is the alkali metal in period 4. The alkali metals are in group 1, and period 4 here, keep in mind, hydrogen is period 1. So we're going to go down to period 4. That is potassium, and the element symbol is K for potassium. There we go. Alkaline earth metal in period 3 is the next one. Alkaline earth metals are in group 2, and period 3 is right here, the third row, and magnesium is there. So here the alkaline earth metal in period 3 is magnesium. The halogen in period 2, well, here again we want to keep in mind hydrogen and helium are period 1. So the halogen in period 2 is actually the first halogen at the top of the group, fluorine, whose atomic symbol is the letter F. Next we have the noble gas in period 5. Start at the noble gases. Helium is the first, and the fifth one down is xenon there in period 5 with atomic symbol Xe. And finally we have the transition metal with Z equal to 44, and here that capital Z refers to the atomic number. So the funny thing about this is we didn't even really need to know that it's a transition metal. That will help orient our eye looking toward the middle of the periodic table, but we could also just go right to atomic number 44, and there it is, ruthenium with the atomic symbol Ru. It's just a little tour of the periodic table there, getting some element symbols down based on descriptions of group names, period numbers, that kind of thing.